Good day everyone, my name is Janel Fernandez, and in this video presentation I will be talking about OSPF, or Open Shortest Path First. So to start, this video presentation is a requirement for our course subject IT6224, Data Communications and Networking in BS Information and Technology of AMAU Online Education. And in this video, we will have three major topics which are single area OSPF, multi-area OSPF, and OSPF tuning and troubleshooting. So we will use our hospital network as a real-world example throughout this presentation, and I will walk you through configurations in using the Cisco Packet Tracer. So first part, our first topic is single area OSPF. This is the foundational form of OSPF, and it is exactly what we will use in our hospital network topology. So let us understand what it is, how it works, and why is it the right choice for our scenario. So what is single area OSPF? Single area OSPF means that every router in the network belongs to exactly one area. And that area is always area 0, or what you call as the backbone area. In this setup, all routers share the same link state database, or the LSDB. Think of it as every router having the exact same map of the entire network. So each router then independently runs Dijkstra's shortest path first algorithm to calculate the best routes to every destination. The administrative distance of OSPF is 110, and OSPF routes appear in the route routing table marked with the letter O. Single area OSPF is best for small to medium sized networks, so exactly like our hospital, because it is simple to configure and very efficient for the scale that we are going to work with. Now let me explain how OSPF actually exchange routing information between routers. So we have five steps processes. So the first step is sending hello packets. So this happens when an OSPF is enabled on an interface. The router immediately begins sending hello packets. These are multicast packets sent to the address 224.0.0.5. Then they announce the router's presence and invite neighbors to form a relationship. Step 2 is forming adjacency. So when two routes exchange hello packets and agree on the same area ID, hello interval and dead interval, they become OSPF neighbors and form an adjacency. So if any parameters does not match, the adjacency will not form. Number 3 is flood LSAs. So once adjacent routers exchange link state advertisement LSA, each router shares information about its directly connected links, interface address, costs, and neighbor relationships. So these LSAs are flooded to all routers in the area. Next step is building the LSDB. Each router collects all the LSAs it receives and builds a link state database. In a single area OSPF, every router ends up with an identical LSDB. So they all have the same complete network. The last step is run Dijkstra's SPF with the LSDB complete. Each router independently runs Dijkstra's algorithm to find the shortest, lowest cost path to every network. The results are placed into the routing table as OSPF routes marked with the letter O. Next, let's now take a look at the key features and advantages of OSPF. Fast conversions. Number 1. This happens when a link fails or a new route appears. OSPF detects it quickly and propagates updated LSAs throughout the network. So for example, a hospital where systems like emergency records and laboratory results must always be accessible. This rapid recovery is essential, and so on. For the next part is classless with VLS support. So OSPF is classless by design, meaning it supports variable length subnet masking. So we can assign different subnets sizes to different parts of the network. So for example, prefix length of 30 for router links and 24 for department networks. Next, Dijkstra's SPF algorithm. Unlike distance vector protocols that blindly trust their neighbors, OSPF calculates the best path itself based on a complete network map. It always selects the path with the lowest total cost. And for the next part is hello packets for neighboring maintenance. OSPF continuously sends hello packets. If a router stops receiving hello from neighbor within the dead interval, it removes the neighbor and recalculates routes automatically. For the next part, we have no hop count limits. RIP is limited to 15 hops. OSPF has no such restriction, so making it suitable for networks of any size. And the last, OSPF is an open standard. This is defined in our FC2328. It works across routers from any vendor, not just Cisco. Now let's begin doing our topology in the Cisco packet tracer. So first, we will drag our devices. We have 4 routers. And the first router will be at the beginning. At the center, we are going to name it with a hospital beam topology. Then under the 2, 3, and 4 routers, we will add 2 960 switches each. We will name this emergency. Then each switches has its their own PCs connected into them. Realistically, in a medical instructor setting, this is what it looks like. We will put serial cords to router 1, 2, 3. Then we will connect them using a serial DC. In the same way, you will connect it into the router 3. We will turn the clock rate into 64,000. The next step, we will use copper crossover to connect the router 1 to 4. Then straight through from router 2 to the switch. In the same way, we will connect the router 3 to the switch 3 with a straight through. Then for the last cable connection is the router 1 to the hospital server. We using the copper straight through. So now we have our final topology. We will now start configuring each routers, and we will start with the first router, R1. For the third router, for the fourth router, Now that we have completed the single area OSPF part for this topology, we will now proceed to the next topic, which is the multi-area OSPF. So our second topic is multi-area OSPF. While single area network works perfectly for our hospital topology and for larger enterprise networks with hundreds of routers, it needs more scalable approach. So that is where multi-area OSPF comes in. So why multi-area? So let me explain why multi-area OSPF was developed. In single area OSPF, every single router must store the LSDB for the entire network. So if the entire network has 200 routers, every router holds information about all 200. And every time any link changes anywhere in the network, all routers must rerun Dijkstra's algorithm. So even routers far away from where the change happens. So this creates three major problems. High memory usage, because every router stores the complete database, and high CPU usage due to the frequent SPF calculations, and slow convergence in very large networks. Multi-area OSPF solves this by dividing the network into smaller areas. Each area runs its own independent SPF calculations. Routers only store the LSDB, or the database, for their own area, not the entire network. So area border routers, or ABRs, summarizes routers between areas, which dramatically reduces the amount of routing information that needs to be shared. The result is lower resource usage and faster convergence per area, and a much more scalable design. Next, in multi-area OSPF, routers have specific roles depending on where they are positioned in the network. An internal router has all of its interface in the same single area. It only maintains the LSDB for that one area, but most routers in a network are internal routers, and they are the simplest type. Next, number 2, backbone router. It has at least one interface connected to area 0. And any router with a presence in the backbone is called a backbone router. A backbone router can also be an ABR at the same time. Next, number 3 is an ABR. What is an ABR? This is an area border router. It is the most important role in multi-area OSPF. An ABR sits between area 0 and another area, as it maintains separate link state database for each, and it connects. ABRs also perform route summarization. They can condense multiple specific routes into one summary route before sending it into another area, which reduces the routing table size significantly. An ASBR, for the number 4, or what we call as Autonomous System Boundary Router. This connects the OSPF network to an external routing domain, such as the internet using the BGP, or another company's network, the ASBR, redistributes external routes into OSPF and sends them out as LSA type 5, which floods to the entire OSPF domain. So what are the LSA types? Now let us talk about their types. LSA type 1 is the router LSA. Every OSPF router generates one. It describes the router's own connected interfaces and links. Type 1 LSAs stay within the originated area, and they do not cross area boundaries. Next is Type 2. Type 2 LSA is the network LSA. This is generated by the designated router, or the DR, on a multi-access network segment like Ethernet. It describes all routers connected to that segment, like type 1. It stays within the area. Next is the type 3, which is the summary LSA. This is generated by an ABR when an ABR wants to advertise a router from one area into another. It sends a type 3 LSA. So this is how inter-area routing works. Next is LSA type 4. It is the ASBR summary LSA, also sent by the ABR. Its purpose is to tell other area where the ASBR is located, so that routers can reach external routes through it. Next, the type 5 external LSA. This is generated by the ASBR itself. It carries routing information from outside the OSPF domain. So for example, internet routes. Type 5 floods to the entire OSPF domain, crossing all area boundaries. So this is why the question asks which LSA type identifies the ASBR to other areas so internal traffic can reach the internet. And the answer is LSA type 4, sent by the ABR about the ASBR. Now, let's do the configuration on our topology for the part of multi-area OSPF. So in the first router, it will start configuring. And then for the following router, for the second router, we will do the same thing. Now for the next router, we have the third router. And for the last router, we have the router number 4. Now that we have completed the multi-area results of our configurations in this section, we will now move to the third part, which is the OSPF tuning and troubleshooting. Now, knowing how to configure OSPF is only the first part. The other half is knowing how to optimize it for performance and how to diagnose and fix problems when they arise. So OSPF tuning and troubleshooting. OSPF gives us several parameters we can tune to optimize its behavior. The first is the router ID. So by default, an OSPF selects the highest IP address on a loopback interface or the highest active interface IP as the router ID. The problem is this can change if an interface goes down. The best practice is to manually set the router ID using the command router 1.1.1.1 or any address that fits the masking inside the OSPF process. So this gives the router a stable, recognizable identity. After changing the router ID, you must use clear IP OSPF process to apply it. The second one is tuning parameter, which is the interface cost. OSPF automatically calculates cost based on bandwidth cost, that is equals in 100 megabits per second, divided by the interface bandwidth. So a fast Ethernet interface has a cost of 1. A serial interface might have a cost of 64. So you can manually override this with IP OSPF cost on the interface to force OSPF to prefer one path over another. Lower cost means preferred path. And then next, we have the hello interval. Hello and dead intervals must match on both sides of a link. So if router A sends hello packets every 10 seconds, but router B expects them every 5 seconds, the adjacency will never form. You can adjust these with IP OSPF hello interval and IP OSPF dead interval on the interface. Next is the OSPF priority controls in the DR or DR-BDR priority or the designated router. Election on the broadcast segments. Setting priority to 0 guarantees that a router will never become the DR. The default is 1 and the highest priority wins. And then next is the passive interface command that prevents OSPF from sending hello packets out of interface that face end devices. So like switches connected to PCs, this saves bandwidth and prevents OSPF from trying to form adjacency with non-router device. Now let's talk about the most common OSPF problems and how to fix them. So the first problem, no neighbor formed at all. The first thing to check is whether the interfaces are up. So use show interface brief and look for up status. Then check whether the network statements are correct. Wrong IP address or wrong wildcard mask are very common mistakes. Also verify that both routers use the same area number. Problem number 2 is neighbor stuck in INIT or two-way state. This almost always means the hello or dead interval don't match between the two routers. Check with a show IP OSPF interface and ensure both sides uses the same values. Also check for access control lists that might be blocking off the OSPF multicast traffic at 224.0.0.5. The next problem that we have is neighbor gets stuck in Xstart or Exchange. So this usually means there is an MTU mismatch. One interface might be set to 1500 bytes and the other to a different value. So fix it by matching the MTU or use IP OSPF MTU ignore as a workaround. Duplicate routers ID are also caused by this problem. So check with show IP OSPF and so on and so forth. Next, the problem number 4 is a neighbor full or no zero routes. Neighbor shows full, but routes are missing. For this problem, check the network statements again. Are all networks advertised? Is a passive interface command blocking the wrong interface? Check with show IP OSPF database once again to see if the expected LSAs are present. Next problem is ping fail despite routes. Ping fails even though routes exist. So for this, check the default gateway setting on the PC. Also verify that the destination route has a route back to the source. And OSPF must work in both directions. Now, let me walk through the most important verification and troubleshooting commands. So for example, show IP OSPF neighbor. This is always your first command to check the state column. If it's full, is what you want. Anything else needs investigation. Next, show IP OSPF. This shows the process details. Router ID, area information, and how many SPF calculations have been run. So if the SPF count is very high, the network is experiencing frequent topology changes. So next part is show IP OSPF database. This part displays the complete linked state database. You can verify which LSAs types are present, which routers have advertised, and whether external routes are being redistributed. Next, show IP OSPF interface or INT, Gigabit Ethernet 00, and so on. So this part, it gives per interface details, including the hello and dead intervals, the current cost, and whether this interface has a designated route, router elected. Next is show IP route OSPF. This filters the routing table to show only OSPF learned routes. So this is faster than scrolling through the full routing table. Next, clear IP OSPF process. This forces a complete OSPF restart, and use this after changing the router ID or after making a major configuration changes. Use it carefully in a live network because it temporarily drops all OSPF adjacencies. And then second to the last is debug IP OSPF events. So this gives you a live real-time log of OSPF activity. Very useful during troubleshooting. So remember to disable it immediately after with undebug all because debugged output consumes significant CPU resources. And that brings us to the conclusion of our presentation. So let me summarize all three topics, but before that, we will check our topology. So as you can see, the result of our configuration is addressed properly because it states that it's up as well as the status are full BDR. So that means the topology that we made is successful. So for the last part, in summary, single area OSPF places all routers in area 0, and every router shares the same LSDP and runs Dijkstra's algorithm independently. It is simple, fast, and perfect for our hospital network that we have made. We verify it with show IP root in the configurations, show IP OSPF neighbor, and ping. Multi-area OSPF, on the other hand, divides the network into multiple areas for scalability. Area 0 is the mandatory backbone. ABRs connect other areas to the backbone and perform more summarization. LSA Type 3 carries inter-area routes, while LSA Type 5 carries external routes from the ASBR. Next is OSPF tuning allows us to control path selection using costs to stabilize the network with a manual router ID, to reduce unnecessary traffic with passive interface, and fine-tune neighbor detection with hello and dead intervals. So remembering that these must match on both sides, and for troubleshooting, always start with show IP OSPF neighbor bash. So check the state. Full means it is good, just like what we saw in our configuration results. Work through the problem step by step, interfaces, network statements, timers, area IDs, and finally end-to-end connectivity with ping. OSPF is one of the most widely deployed routing protocols in real enterprise networks. So understanding it deeply, not just how to configure it, but why it works the way it does, is a critical skill for any network engineer. So thank you for watching this presentation, and I hope that it has given you a clear and complete understanding of how OSPF work. This is all the summary and the entire presentation of the course project in Data Communications and Networking IT6224. My name is Janel Fernandez, and thank you for watching.